Dear students, this is our 22nd lecture on medicinal chemistry and 8th lecture on antiviral agents and third lecture on COVID-19. As you know that COVID-19 disease was first identified in China, Wuhan in December 2019, and till date more than 7 million people have died because of this pandemic. In the previous two lectures, I have described about the details of what this COVID-19 disease is, and then the structure of the virus and how it acts in our body. So mechanism of action of replication of this COVID-19 virus has been described in this lecture. Then for the cure of COVID-19, some drugs which were already existing as either antiviral drugs or for some other diseases, they have been used because no new drug has yet been synthesized particularly for COVID-19. So in this lecture, I have described about a few drug synthesis, of which we have seen how hydroxychloroquine can be synthesized in the second lecture, then lopinavir, how it is synthesized, and remdesivir. So these are the three important drugs which have been used for one or the other purpose to control COVID-19 drugs. And in the present lecture, we will discuss the other important drugs. First among those is ritonavir. Ritonavir or Norvir is synthesized starting from methyl and benzoyl oxycarbonyl alphenylalanine methyl ester. So you can say this starting material for the synthesis of this drug is an amino acid ester derivative. So through common organic functional transformation reactions, we can transform this alphenylalanine methyl ester derivative into the drug which is called as ritonavir. The details of the transformations, they are like this, that when this alphenylalanine methyl ester undergoes reduction with lithium aluminum hydride, then this ester is transformed into this primary alcohol. So phenylalenol derivative is synthesized by reduction of this alphenylalanine methyl ester. Then on reaction with the COCl2 in presence of DMSO at very low temperature of the order of minus 60 degrees centigrade, this primary alcohol is oxidized to the corresponding aldehyde. Then this alphenyl alanine aldehyde derivative, uh, this reacts in presence of zinc dichloromethane, VCl3, and THF as solvent, and reductive first zinc causes the reduction of this, and then dimerization in presence of this, we will get this type of 1,6-diphenylhexane 3,4 diol derivative like this. And the reaction is selective to give us this type of alpha diols. And these alpha diols on reaction with alpha acetoxy isobutyryl bromide, this one. So this in the presence of dichloromethane and hexane as solvents, one of the hydroxyl group will become esterified and other hydroxyl group will become halogenated. So we are from here, and this acetoxy group from here is transferred to the diol derivative, and we will get this type of 4-bromo 1,6-diphenyl hexa 3-ol acetate ester derivative as the product. And this product undergoes formation of epoxide at this place in presence of sodium hydroxide as a base and 1,4-dioxane as the solvent. And then this epoxide undergoes reduction in presence of THF and trifluoroacetic acid to give us, and not only opening of this epoxide ring take place, but also hydrolysis of these amidic bonds also take place, and we will get so hydrolysis over here and hydrolysis over here, in addition to opening of the epoxide ring, will lead to the formation of optically active 2,5-diamino 1,6-diphenyl hexane 3-ol derivative is formed. Then this derivative again reacts with this carbonate derivative, and we will get this type of N substituted amide ester will be formed, and this amide ester on reaction with this amino carbonyl valine derivative will undergo uh, reaction with this addition of this to this amino group will lead to the formation of retinovir as the product. So this whole process converts alphenylalanine methyl ester derivative into retinovir, which have been used for the treatment of COVID-19 also. The next important drug is dexamethasone. Dexamethasone was mainly used for treating critically ill COVID-19 patients which were on ventilator, and they were given the specific doses of dexamethasone, and it was found that mortality rate became about 1/3 when the patients they were given dexamethasone. So that means dexamethasone was also one of the important drugs which was given for treatment of COVID-19 patients which were critically ill. So main reason for this was that dexamethasone is having very well-known anti-inflammatory properties, and this is basically a steroidal drug, corticosteroid drug, uh, which has been used for a variety of medical disorders. So this drug is a derivative of cortisol, that is hydrocortisol, cortisone, uh, which is 6 alpha methyl reginolone, this one, or tigogenin. So both these they are basically steroidal derivatives from which we can synthesize dexamethasone. So dexamethasone, which is a steroidal carboxylic acid, you can say, at the side chain, and having alpha beta unsaturated ketone moiety in addition to hydroxyl functional groups. This drug can be synthesized either from this tigozanin or 16 alpha methyl progenolone. So both these they are also naturally occurring compounds, and because the abundance of this compound is more in nature, so this is most commonly used for production of dexamethasone acetate. So synthesis of dexamethasone starts from ticozanin. So when ticozanin is treated with acetic acid at high temperature of the order of 200 degrees centigrade in presence of chromic acid, when this is heated, the ring opening of will take place at this to give us this type of ketone. And then this ketone, when this is treated with methyl magnesium chloride in presence of cuprous chloride and acetic anhydride acetic acid, basically Grignard reaction will take place. So this will add across this keto group as well as this alkene group to give us this type of alpha keto alcohol as the product. And this alpha keto alcohol undergo bromination in presence of bromine and dichloromethane, followed by hydrolysis with HCl and acetic acid to give us this hydroxyl group is transformed into a bromo group. So alpha bromo ketone is formed. Alpha keto alcohol is converted into alpha bromo ketone, and then this alpha bromo ketone undergo acetylation to give us alpha keto ester in presence of potassium acetate and acetone, and then this undergoes in presence of calcium hypochlorite, oxidation of this hydroxyl group take place, and this is converted into this type of ketone. So this ketone ester then in presence of HCl acetic acid and bromine undergo dibromination at the alpha positions to this ketone, and this dibromination undergo dehydrobromination at these two places, H from here, Br from here, H from here, and Br from here. Dehydrobromination take place, and we will get this type of alpha beta unsaturated ketones in presence of calcium carbonate, sodium bromide using DMF and 6% water. Then hydrolysis of this acetate group take place in presence of base, and this hydrolysis leads to the formation of this beta keto alcohol in presence of Pastalotia florens, which is a fungi, and then this sodium hydroxide and water will hydrolyze this into the alcohol, whereas hydroxylation at this carbon will take place in presence of this fungi, that is Pastalotia florens will produce this hydroxylated product. And then this in presence of sodium acetate acetic acid will again convert this hydroxyl group into the acetate group, and dehydration will take place at this these two carbons, OH from here, H from here. We will get the dehydrogenated product. And then in presence of perchloric acid and N-bromoacetylide in presence of sodium acetate, the epoxidation at this carbon-carbon double bond will take place, and we will get this epoxide, and this epoxide on reaction with HF in presence of chloroform and THF will lead to the introduction of chlorine at this C19. So we will get this dexamethasone acetate as the product, and this dexamethasone acetate on hydrolysis in presence of base potassium carbonate in methyl alcohol will lead to the formation of dexamethasone by hydrolysis of this acetate group into the hydroxyl. So this is how we can synthesize dexamethasone starting from tegozinone. Then next is oseltamivir. Oseltamivir, which is also called as Tamiflu drug, which is sold under this brand name Tamiflu by Hoffmann La Roche, is basically an anti-influenza drug which is given for the patients of anti-influenza A and influenza B. So this is a very important drug, and this has also been used for the COVID-19 patient. And because of the importance of this drug, this has been synthesized through many methods by many scientists. The most commonly used starting material for synthesis of this drug is shikimic acid, which is extracted from Chinese star anise and recombinant E. coli. And there are three different stereo centers in the molecule, and only one of the eight stereoisomer is the desired isomer which act as this drug or oseltamivir. So because of the stereochemistry requirements, it is very crucial to synthesize this drug in pure form. So that is why there are different types of methods which have been given by different scientists. So the first synthesis was done by Gilead Sciences. The firm Gilead Sciences has synthesized either from cunic acid or shikimic acid. So what they have done is that they have started from shikimic acid, and through etherification of these groups followed by methylation and ketalization, they have converted the shikimic acid into this shikimic acid ester derivative, where this hydroxyl group is methylated, and these two hydroxyl groups, they undergo ketalization with pentane 3 bone, followed by esterification at this carboxylic acid group. Then this ketalized ester shikimate undergoes opening of this ring with TiCl4 and triethylsilyl hydride in presence of TCM at low temperature of the order of minus 34 degrees centigrade for 2 to 6 hours. Then ring opening will take place at this place, and this will be converted into hydroxyl group. This will be converted into an ether moiety. So after the ring opening of this, the hydrolysis of this methylate, then this hydroxyl group will be converted into an epoxide ring with the removal of this mesylate group, we will get this type of epoxide. Then this epoxide undergoes the formation of azide when this is treated with sodium azide in presence of ammonium chloride under aqueous ethyl alcohol at 60 degrees centigrade. So ring opening of this epoxide in presence of sodium azide will lead to the formation of a mixture of these two azides in ratio of 9 to 1. Then this azide undergo formation of azirine ring, three-membered aziridine ring in presence of triphenylphosphine and triethylamine. Then this undergoes ring opening again in presence of sodium azide, sulfuric acid, DMSO, and we will get this type of azidamine. Then this amine undergo acetylation in presence of acetic anhydride. So N-acetyl amine will be formed, and this acetyl, sorry, this is wrong. Here it should be azide. So N-acetylamine azide is formed. Then this N-acetylamine azide undergo a reaction with tributyl phenyl and followed by reaction with H3PO4 in ethyl alcohol to give us oseltamivir as the product. Then another method which was given by Kauf and Trossady, which is called as Kauf-Trossady synthesis. This again starts from shikmic acid. Uh, the first three steps are same as we have seen in the previous method, and after the formation of this ester, this under Hunter conditions again in the same way is converted into this type of methylated uh, ester. Then this again undergoes epoxidation in the previous way, and after this the steps they are different. Then allylamine reacts with this epoxide, and ring opening leads to the formation of this type of anilyl substituted amine derivative, which undergoes reduction in presence of palladium on charcoal, and this is reduced to amino group. So this amino alcohol then undergoes condensation with benzaldehyde. So the corresponding shift base at this position will take place. So we will get this type of shift base, and then the methylation of this hydroxyl group will take place, and then on reaction with this shift, this allylamine, which will attack over this with the removal of this shift base, we will get this type of three-membered azidine compound. And then this shape base which was produced at this place will undergo addition to this group, and we will get this type of uh, an allyl substituted amine with the shape base. Then this will undergo hydrolysis, carbon nitrogen double bond, and amine group will be regenerated. Then this amine group will undergo an acetylation in the presence of acetic anhydride, as we have seen in the previous synthesis. And then ethyl amino alcohol will react with this for the hydrolysis of this. In presence of palladium and charcoal, we will get Tamiflu as the product. Then next is Curie synthesis, which was achieved in the laboratory, and here The starting material used for the synthesis of Tamiflu, they are different than the chicmic acid or cunic acid. So here the method starts with the reaction of butadiene butadiene with this acrylic acid ester of 2,2,2 trifluoroethanol. So when these two in the presence of uh, Kore-Bakshi-Shibata catalyst, CBS catalyst undergoes asymmetric Diels-Zelter reaction. So this is our diene, this is dienophile. So enantioselective cycloaddition reaction or asymmetric Diels-Alder cycloaddition take place to give us this type of ester. And this ester in presence of ammonia is converted into the corresponding amide by hydrolysis attack nucleophile attack of this nitrogen on this carbonyl with the removal of this trifluoroethanol. Then this amide in the next step is converted into this type of lactam through iodolactonization in presence of iodine with followed by trimethyl SLIET reflate. So this will produce break this iodine and lactamization will take place to give us this type of lactam. And this lactam in presence of Bock anhydride will be converted into this N-Bock product. N-Bock lactam will be produced and this N-Bock lactam will undergo an elimination reaction. H from here, I from here, it will generate a carbon-carbon double bond in presence of DBU base. This 1,8 di as a bicyclo undecane 7 in TBU will catalyze this dehydroiodinization, that is elimination reaction. Then this alkene lactam will react with N-bromosuccinimide which will give us the corresponding bromide, and this bromide then again will undergo reaction with cesium carbonate in ethanol to give us diene ethyl ester as the product. So this diene ethyl ester uh, then will react with SNBr4 in presence of N-bromoestamide to give us this type of N-Bock N-acetate derivative. So this N-acetyl group will add to one carbon and bromo will add to the other carbon, and reaction is enantioselective in nature and we will get this type of optically active product. And then this will be converted into this type of aziridine in presence of strong base like potassium hexaethyl silazide KHMDS. This will convert this nitrogen will attack this carbon with the elimination of Br from here, H from here. We will get this type of aziridine as the product. And then ring opening of this aziridine will take place in presence of 3-pentanol. So 3-pentanol as a nucleophile will attack at this carbon and this aziridine ring will open up to give us this type of ether, and then this ether can easily be converted into Tamiflu on reaction with phosphoric acid. So this is how we can synthesize Tamiflu when starting with this Diels-Alder reaction of 1,3-butadiene and 2,2,2 trifluoroethyl, and this synthesis is called as Fourier synthesis. Then is one more synthesis was given by Sebaski, and this is called as Sebaski synthesis. And here also the starting materials are different than the previous synthetic methods. So here the Sebaski started with this type of aziridine. When this aziridine was treated with trimethylsilazide, the opening of this aziridine ring take place, and this reaction take place in presence of a chiral catalyst, and this is converted into this type of azide. And then this azide the this azide amide group is converted into N-Boc in presence of Boc anhydride in DMAP, and then this undergoes hydrolactamization as in the previous synthesis we have seen in presence of iodine and K2CO3, and then elimination, hydro H from here, ido from here, elimination to generate a carbon-carbon double bond in presence of DBU in the same method as we have seen previously. Then protection of this nitrogen on reaction with Boc anhydride N-Boc derivative is formed. Then this N-Boc derivative is converted into this type of N-acetyl amide by reductive acylation through by reductive acylation through this dimethylpyridine, followed by reaction with cesium carbonate in ethanol. This is then opening of this lactam derivative take place, and we will get this type of N-Boc derivative. Then oxidation of this alcoholic functional group take place in presence of DMP, Des-Martin periodinane. So this oxidation take place with DMP. Then this undergoes cyanophosphorylation with diethyl phosphorocyanamide DEPC. So this will add across this keto group. So this cyanophosphorylation will take place at the keto group, and we will get this type of cyanophosphate derivative. This cyanophosphate, when reacted in presence of seal tube in toluene, then dephosphorylation take place, and we will get the corresponding unstable beta allyl phosphate, which will be converted into the corresponding alcohol on reaction with ammonium chloride in water. And then this will undergo Mitsuno-2 reaction in presence of that and triphenylphosphine and paranitro benzoic acid, and the beta alcohol will be converted into alpha alcohol. So basically this is used for inversion of configuration of this hydroxyl group, because we require this configuration for the synthesis of oseltamivir. Then this will be converted into the aziridine derivative by a second Mutsunobu reaction, and then again in the same way as we have seen in chorusynthesis, ring opening of this will take place with the 3-pentanone, and through this intermediate, uh, which on reaction with phosphoric acid will be converted into O-saltamivir in the same way as we have seen it with the chorusynthesis. Then latest among the synthesis for O-saltamivir is Hayashi synthesis. This was given in 2009 by Hayashi, which is an efficient, low-cost synthetic route which have been given, where this O-saltamivir is synthesized natio-selectively through three one-pot reactions. So the first one-pot operation is reacting this alkoxyaldehyde with this nitroalkene. So this alkoxyaldehyde and nitroalkene, they in the presence of diphenyl prolinol silyl ether, this as the organocatalyst undergoes asymmetric Michael addition. So asymmetric Michael addition take place to give us the enantioselective Michael adduct, and this Michael adduct then undergoes reaction with diethyl vinyl phosphate derivative. This one to give another Michael adduct, which on domino Michael reaction and Horner Wedgwood-Hammond's reaction gives us the product this T through the third step, which is reacting with the cesium carbonate in ethanol, and followed by addition of paratoluene thiol. So we will synthesize this type of derivative in 70% yield, and this is purified through column chromatography. So this nitrothiol derivative, which is synthesized in first one pot operation, then undergoes reaction with dichloromethane and trifluoroacetic acid for 2 hours, followed by reaction with phosgene, oxalyl chloride, and sodium azide to give us this ester is converted into ketoazide as the acyl azide as the intermediate for the synthesis of O-saltamivir. Then in the next one pot operation, this acyl azide is reacted with acetic acid in acetic anhydride for room temperature, and then after evaporation a residue is formed which undergoes reduction with zinc in trimethyl silyl chloride at 70 degree in presence of ethanol as solvent, and then this will produce the amine on reduction, and this amine then undergoes acetylation with ammonia and ethyl alcohol to give us this type of a product which is O-saltamivir. So reduction of nitro group will also take place with zinc to amine. So this is all about the references which have been used for preparing this lecture. Thank you very much.